Okay, so in the next few minutes, I want to show you an insight into modern techniques in electron microscopy, transmission electron microscopy towards atomic resolution microscopy. Before I do that, I would like to acknowledge the people that contributed in some form to all the material that is presented on the slides later on from the Weizmann Institute here. And also collaborators, you see the people from the SciTech here, and some collaborators from Tel Aviv University and Jülich. So for transmission electron microscopy, we've seen two major breakthroughs in the last 2 decades. One of them affected mostly the material science microscopy, the other one the life science microscopy. For the material science microscopy, it was the successful implementation of aberration correctors and spectrometers, which put us into the position to look inside matter atom by atom. And the developments in this direction were just awarded by the Kavli Prize for Nanosciences this year. Equally important for the life sciences is the resolution revolution, which was brought about by the invention of new detectors, which are single electron sensitive and capable of counting single electrons at low noise. And this made possible the resolution revolution, which ended up in the very successful single particle analysis work. For material science, it's, as I said, mostly the aberration correctors, which made a big impact. And I was happy to be part of the development around the prototype microscope in Jülich. Back then, I entered just shortly after the Volkswagen project, which was run by Harald Rose, Max Heider, and Knut Urban. And they developed the so-called Hexapole type corrector, which is seen here in the prototype microscope as the silverish part. And the effect of this corrector is to reduce the so-called spherical aberration, which produces an image artifact which is related to overfocusing of large angle beams in the objective lens. And this, in the past, for regular microscopes, led to the fact that if you wanted to image a point in the object, you would image it only as a disk of confusion in the image plane. But when you have correctors, these multiple correctors of the hexapole type, then you can reduce this effect and you can improve quite to a big extent the resolution. So the advantage in terms of the resolution was that for a typical 200 kV microscope, you could increase the resolution from about 2 angstrom to the 1 angstrom range, which means that it becomes possible to see atoms. So nowadays, this technology is commercialized, and in the meantime, about 900 of these correctors have been installed worldwide. And 97% of these are just this Rose-type hexapole correctors, exactly like in the prototype microscope. This is one of the commercial type instruments. We are happy to have it here in the Weizmann Institute. It's a double corrected Titan Themis Z of Thermo Fisher. And it has 2 correctors, one for probe forming lens. That's when you want to do scanning transmission electron microscopy with a very finely focused electron beam. And another corrector, which is used when you do TEM, that means you have wide field illumination and you produce an image of a large area of the sample at one time. And with these aberration correctors now we go to deep sub-angstrom resolutions. The STEM probe size can be better than 60 picometers in this case, and a TEM resolution better than 70 picometers. So here's just one example, a typical benchmark gallium nitride dumbbells. These are closely neighbored atomic strings of gallium atoms in this case, basically. And their separation of 70 picometers is easily seen in a direct image of the microscope. And in the Fourier transform, you see even 43 picometers, and for comparison, the hydrogen, the Bohr radius of hydrogen is 52 picometers. So we are in the deep sub-angstrom range. Image resolution is not everything. A modern microscope should be better considered as a small lab-scale beamline with accessories and components attached to it, and with multiple detectors to catch the signal which is produced by a sample as a response to the fast electron. So for instance, we have monochromators in order to reduce the source width, the emission width of the electron source. Typically in a field emission microscope, you have an energy spread of the source, which is around 1 electron volt. This is for a Schottky type emitter. For field emission emitters, cold FEC emitters, you can have something like 0.3 electron volts. But with a monochromator, you can bring down this width to, in our case, 70 millielectron volts, which comes very handy for reducing the chromatic aberration for imaging at lower voltages, or to do high resolution energy loss spectroscopy. And I will show a few examples later on. If you push it to the limits, that's what has been done by a company in the US, the Neon company. They pushed the monochromation to the limits and go down to less than 10 millielectron volts, where you can access later on in spectra then also vibrational properties of samples. Another important addition to the microscopes is fast image detectors. We see more and more of this technology coming up. So one example is high frame rate CMOS cameras. These are quite often designed with a scintillator in order to be responsive. If they are without scintillator, then they are capable of detecting single electron pulses, and these so-called direct electron detectors, they are used very much in low-dose applications now. Their dynamic range is limited, but their speed is formidable, and electron counting contributes to reducing the noise in the detection. Another recent development is the so-called hybrid pixel detectors, where the sensor is bonded, back bonded by the amplification circuit. So each pixel has its own amplification circuit. And these detectors are characterized by single electron sensitivity plus high dynamic range. It comes at the moment for the price of a little number of pixels. But I will later on show examples of new techniques that you can do with these detectors, the so-called 4D STEM techniques. These detectors are all quite important, but the catch is a little bit that there is not one detector for all applications. Then you have high resolution energy loss spectrometers, which allow you to analyze the energy that is lost by the fast electron to the sample. So you can measure, for instance, characteristic transitions in the matter that you probe to do chemical analysis. And you can also, using a monochromator, map out optical transitions at low energies. And we will see examples of that later on as well. In addition, for spectroscopy, you can analyze the X-rays that are emitted upon an inelastic scattering event in the sample. And the probe current densities of aberration-corrected microscopes are that high that you can do this with a spatial resolution right now into the atomic scale. So here we see an example of an indium arsenide antimonide nanowire, and we see the atomic configuration of this broadside lattice across a twin defect here, and we see also the doping with the antimony in this lattice, and all of that with atomic resolution. So let me switch to just a few examples, a gallery of examples before I come to 4D STEM and yields. This is because a common theme of my former advisor in Jülich, Knut Urban, was that atoms must be visible. So in any kind of talk of microscopy, you need to see atoms. First example is of Misfit layer compound nanotubes. This is the topic of Recherche 10. And these Misfit layer compound nanotubes are composed of 2D inorganic TMDC layers, which are folded to tubes with alternating chemical composition. So here's an example of a cerium sulfide, chromium disulfide nanotube, where we see the outer tubes of the nanotube in atomic resolution and this high resolution TEM image that was taken back then in 2014. The TEM image, although it had atomic resolution, didn't really show very clearly the structure. So you need to know a little bit about the structure in order to assign the lattice structure like I did here on this slide. Now, with optimizing all the parameters of the system and going to slightly better imaging conditions, we can achieve true structure resolution, like here shown on the STEM bright field TM image, where we see the alternating structure of the hexagonal tantalum sulfide and the distorted rock salt layers of yttrium sulfide in this case. And you can assign the structure, like in a projection, to a number of shells on the outer range of the nanotube. So this is seeing atoms directly and seeing what the structure is. Of course, we want to go further, doing spectroscopy on this and starting to map out chemical bonding in these systems. Another example here is of calcium fluoride nanoparticles that are used in NMR, in vivo NMR studies. So these fluorides have the fluorine as the NMR marker. And in order to enhance the fluorine signal for NMR, these particles are doped with samarium. And in the TEM image, you don't really see the samarium doping, but you see it very nicely here in the high angle annular dark field image, which catches the large angle Rutherford scattering of the heavy samarium atoms, and they light up like stars in the dark night sky. In EDS, you also can see the signal of the samarium here in blue, opposite to calcium in red. And from these EDS maps, we learned that the samarium is actually not built into the nanoparticles, but it's decorating the nanoparticles on top of the surface. So this is some information which is important for the activity of the samarium towards the fluorine resonance in NMR. Another example is of 2D layer TMDC materials. So here is a study together with a group in Tel Aviv, Ariel Ismach, and we are trying to discover or find out about intrinsic defects in MOCVD grown tungsten disulfide. And here on the left-hand side, we see a STEM image of tungsten disulfide. We see the lattice, and you probably can spot all the dark spots inside the lattice, and these are actually point defects. Turns out at slightly higher magnification here that these are tungsten sulfur 3 vacancies, as they have been reported for molybdenum disulfide in the literature. What we can add here is that beyond the still images, we can do dynamic studies of these defects, all keeping in mind that, of course, we have an illuminating beam, which also puts energy into the system. But if we look at fastly recorded STEM images of these defects, then we see that basically they are sitting nicely in the lattice. And they are pretty stable over a long time of irradiation. And if we look a little bit closer, even in higher magnification, in this next movie, then we see what happens actually with these defects. Here we see a single tungsten atom which escaped from the lattice position, and due to the fact that we have multiple sulfur vacancies, it cannot really hop back into the position. It's not finding any stable position inside the defect anymore, but it's rather going around next to the lattice, and it's hopping between threefold coordination states. So this is a looping movie taken over something like 30 seconds in a microscope. So it's a little bit speeded up for display here. But it already shows that there is also dynamics in the defect. And since 200 kilovolts that we used here is pretty high energy, and it might interfere with defect coordination, we also went to TEM mode at lower voltage, which has less damage and produces less sulfur vacancies. And here's an example where we study the dynamics of the defect in a slightly different way. So we do a dynamic experiment in the TEM. In this case, it's a very fast focal series, which was taken over 4 seconds. In the past couple of years ago, this was only possible within a recording time of, let's say, a minute or 2 minutes. So here we are looking very fast. So this is an animation in real time of the focal series that we take on the microscope. And from that we can reconstruct, for instance, the area around this defect, this vacancy defect, with phase retrieval methods. And the result is shown here on the right-hand side. We clearly spot the lattice of the tungsten sulfide. But we can also see more inside the defect area here. We see that there is background intensity, and this is because of the sulfur, but the sulfur is not really bonded into fixed positions. That means in the defect, actually, during this 4-second exposure time, the sulfur also changed positions, and it's not attached into one bonding configuration, but it also flips between the different configurations. And there is also one more detail, which is quite curious, and that is actually that in many cases, the tungsten atoms, they are not really gone. So if you look at the animation here, then this is one of these defects, but the tungsten atom is still there, but it's just weakly bonded, and it has a much higher de Bavella factor, so therefore you hardly see it. Okay. Good. So this brings me to the next topic, one of the more advanced topics that is being pushed very much right now in the field, and that's so-called 4D STEM, momentum resolved STEM, as other people call it. And this is a step towards multidimensional microscopy. I will explain a little bit more what this means in a second. So the idea is that with multidimensional data, you can measure properties better than before concerning nanotechnology, like measuring strain, polarization, or composition of materials, measuring electric fields or charge density or charge transfer. And for biology, you can optimize contrast versus the dose. And so how does it work? In a classical STEM experiment, you would have your STEM probe, which scans over the sample, and for each sample position, you would take on, for instance, an annular dark field detector, the total scattered intensity falling onto the detector as one value. And in 4D STEM, in difference, what you do is that you raster the sample, but for each sample position with a pixelated camera, you take a full diffraction pattern. So what you collect in this case is the XY information of the scan on the sample, plus the momentum information, the momentum transfer information in X and Y direction. And therefore it's called 4D STEM. So What it looks like in reality is shown here on this slide. So this is actually already a fake image taken with a so-called virtual detector of cesium lead bromide. In this case, this is a pixel area of 256 by 256. So behind each pixel here, there is one diffraction pattern. We have 65,535 diffraction patterns. And some of them are shown here in this animation. This is what you see on the detector when you're scanning in this small area. So for each pixel, you get a diffraction pattern. What we can derive from these 4D data sets are so-called virtual images. So we can take virtual detector masks, put them onto each of the diffraction patterns, and then transform back to image space and get the according image which shows the scattering information in that range. So I did this here for the cesium lead bromide. There's a virtual bright field image, virtual angular dark field image, and then in the high scattering angle range, the virtual hard image. Now there's an easy way to segment all the information in the scattering angles that is encoded. So you plot the detector signals in a scatter plot against each other in a three-dimensional diagram. And then you can see that the signal branches into different clusters, and the clusters correspond to the scattering strength of the materials. So here in this area, if you transform back into image space, the cluster of scattering information in this range, then you will see in the image part only the only the lead atoms lighting up. With this cluster here in green, you see only the cesium atoms. And this gives you an easy way to segment your images and to analyze for actually chemical composition. You can push this a little bit further. We used before symmetric detectors. Here we use asymmetric detectors, virtual detectors, and then you can analyze, for instance, the momentum transfer in the diffraction pattern, which gives you information about electrical fields, for instance. And here's one example from a colleague in Jülich, Knut Müller-Kaspari, who did this on molybdenum disulfide, and he could map out by the deflection of the diffraction patterns, pixel for pixel, the electrical field which is behind the deflection. Of course, these are mostly the nuclear Coulomb fields that you map out, but the idea is to go towards mapping bonding information as well. What else can you do with the 4D STEM? Since you have diffraction patterns, you can basically do zone axis orientation mappings and then measure strain or lattice bending. And we did this here for the indium arsenide antimonide nanowires, which showed twinning, and we can relate the twinning in the structure to small deflections of the diffraction pattern, which is related to orientation tilts of the lattice.
Sorry, Lothar, you have 5 minutes, and I would like to also ask audience to put questions, to write question into question and answer slot. Thank you.
Right. Fine. So let me skip over the next example of nanodiffraction then and go directly to the application of high resolution yields. So here we use a monochromated beam and a high resolution energy spectrometer in order to map out optical transitions that are induced by the fast electron in the sample. First example is of excitons in transition metal dichalcogonides. This is a project which is about well, the quest for interlayer excitons and Moire TMDCs. And this is just a preliminary experiment to map out excitons in these stacks of, in this case, tungsten selenide and molybdenum selenide. That we see here in the images and also in the EDS maps. We see that in the central region we have a stack of molybdenum selenide on top of tungsten diselenide. And here we see high resolution energy loss spectra, which in detail show as indeed the excitonic excitations of A and B excitons in the two materials, which means that with the high resolution EELs we have a key in order to measure spatially resolved excitonic excitations in these 2D layer materials. And the next result, I don't need to go too much into detail here because there are two more presentations that are coming up in this webinar about this. It's about plasmonics and the quantum coupling between a plasmonic resonator, silver bow ties in this case, and quantum dots. So here in this slide we see the maps of plasmonic resonator excitations in silver bow ties measured by EELs, and in the project actually we went a step further. Rather than measuring just the resonances of the plasmons, we placed quantum dots in the vicinity of these plasmonic resonators. And if there's a coupling, then we expect to see a splitting, a Rabi splitting, if this coupling is strong in these plasmonic resonances. And I just give the message here because I suppose that I anticipate that Lothar Houben will talk about this in more depth later on. We were actually successful in this project to measure the coupling between a quantum dot or between quantum dots and a dark plasmonic mode, which is only accessible by near field excitation, by the local excitation in EELs. And with this, I'd like to summarize and maybe give a little outlook. So modern TEM instruments are lab-scale beamlines for imaging, diffraction, and spectroscopy on atomic scale. And with the advent of all the modern accessories like aberration correctors and fast cameras and detectors, we hardly have any limitations in terms of technology anymore. But in most cases, the samples are limiting. And that means the technology is now pushed in order to develop better detectors that are counting every electrons, making use of every electron, and the detector efficiency is a key factor. So the latest advancements in the field are, for instance, using hybrid pixel detectors for EELs, for the core losses, for chemical mapping, and also in this case for the vibrational spectrum mapping of Q-dependent EELs. And these are very exciting new developments, and it comes only about with new detectors. So with that, I'd like to thank you, and we can come to the questions.
Thank you very much for an interesting talk. And now there are two questions. The first one, I will read it. As I knew from literature, it's hard to deal with the most unstable phases of 2D layer materials like 1T, 3R. Is it possible to do imaging of these unstable phases of 2D materials using HRTEM, high resolution TEM?
Yes, it's possible. I mean, if you go back to the slide that I showed for the nanotube, there it was pretty easy to see whether you have a prismatic coordination or a 1T coordination. So this would be the slide to show here. It's pretty clear that for the tantalum sulfide, you have a prismatic coordination and not a 1T coordination. Okay, and there are also the literature examples which show nicely that you can discriminate between 1T and
okay.
H or 3R.
Thank you. And the second question is, I'm curious to know if it is possible to image magnetic 2D molybdenum fluoride, it jumped me, molybdenum fluoride, where is it?
Okay,
molybdenum fluoride using HRTEM. Yeah.
HRT,
Or chromium, germanium, telluride, similar stuff.
HRT are not, but the 4D STEM technique would be a candidate to do this. And also there's the technique of electron holography, which would be also interesting in that respect. So for sure there is, it's a challenge because these magnetic fields are pretty small. The effect on the electron beam is small, much smaller than the effect of the Coulombic potential of the nuclei and the material. So therefore you're trying to look for a signal which is something like 1% of the total signal, and then you're always dealing with noise and issues with noise. And that's again a reason to go for the very modern low noise single electron capable detectors, detecting capable detectors.
Okay, there are other two questions, but I will just go for one. Carbon contamination during WS2 and OS2 measurements in TEM. So carbon contamination. How do you clean these samples before measurements?
It's a problem. Basically, the best thing to do would be to heat inside the microscope before you observe. That means you heat up the sample to something like 600, 700 degrees and release the carbon. We didn't do this here, but it's a very good point. It's always an issue, and this is one of the nasty practical issues.